Super. Thank you so much. I appreciate that. So I look forward to a discussion this morning today about architecting the future. And we'll be focusing, of course, on topics that relate to middleware, although many of the topics here are broader than middleware. So let's go ahead and start. First of all, it's pretty clear that we have an ever-growing dependence on software-reliant systems that make it very important to continually innovate in terms of our software engineering theories, our tools, our practices. And obviously, it's also the case that software has become quite ubiquitous today in every sector in the economy and society, and therefore we need to be able to find ways to develop and assure software continuously and be able to insert new capabilities into the field as quickly as possible. And not surprisingly, given the context of this talk, advances in middleware are crucial to support these goals. There's also a number of shifts that are taking place over the past few years and continuing on into the foreseeable future that require new research. One of the things that's really happening these days is we're trying to rapidly deploy safety and mission-critical systems that require advances in software. And as you all know, it's difficult to be better, faster, cheaper all at the same time. And that's one of the things we're wrestling with, how to be better, faster, cheaper, not just two or one of those three. And therefore, it's important that we think about ways to intentionally innovate and continue to get better as a discipline and have our techniques and our tools and our practices find their way into practice. So as part of this effort, I've been involved with Carnegie Mellon University's Software Engineering Institute over the past few years to work on a study that will reevaluate and redefine how we develop and maintain software. And this effort has really been designed to help catalyze the research community to be able to think about what's our longer term vision and to try to come up with a roadmap of what's happening and what's coming next so we can be more effective in building the next generation of software reliant systems. So that's kind of those are the themes of the presentation today. You can get access to this presentation at the link on this slide. I will share the PDF version of these slides so you don't have to try to copy this down. But if you Google the Architecting the Future of Software Engineering, you'll find this at the Software Engineering Institute's website. So again, just to kind of recap the motivation for this, software and especially middleware has become vital to the competitiveness, innovation, and security of companies, of universities, of nations, of people. And this is true across the board in terms of healthcare, education, national security, entertainment, of course. And there's a lot of value, a lot of economic value that's locked up in these areas. If we want to continue to do our job effectively, especially as researchers, we're going to need to figure out how to identify what the future challenges are to engineer software-reliant systems. And what we've done and what we need to continue to do is come up with a roadmap that will help to drive intentional advances in foundational principles to support the different types of systems that we're working with. So some of the key new types of systems, as we'll talk about in just a moment, are intelligent systems, autonomous systems, safety-critical, mission-critical systems, data-intensive systems. These are all things that are trends that started a few years ago and are going to continue into the foreseeable future. Something else that's important, and since this is a doctoral symposium, this is important for future researchers in this area, it's also essential we continue to raise the visibility of software to the point where it receives the sustained recognition from funding agencies and from companies and governments and other sources of sponsorship that's commensurate with the importance that these advances have in terms of security and competitiveness. In the field, certain fields do a very good job of finding ways to get funded. The medical research field in the United States, for example, is very effective at getting sustained funding. Computing, and especially software and middleware, tends to come and go. Sometimes people think that industry is going to do it all. Sometimes people think that government needs to help invest. We certainly need to find a way to invest in education, and we need to have effective researchers to help be the leaders and the teachers of tomorrow. So making sure that people understand why this is valuable is crucial to its long-term success. And as part of that, we're not going to be able to do this alone. We as people in academia can't drive innovation without a partnership with government, who provides a lot of the funding, and also industry, who provides lots of the interesting challenges and some of the funding, and certainly places for our students to go off and get careers if they don't all become university professors like some of us. So let's talk about some of the new types of systems that require advances in R&D. So highly adaptive mission systems, for example, driverless cars or autonomous vehicles of all sorts, where the system needs to be able to adapt its behavior based on the environment it's encountering, not always with human intervention. We also need to be able to deal with systems that perform data fusion at a huge scale. Think weather forecasting. It's really remarkable how much more accurate weather predictions has become, but it's not perfect. It's more of a science than it used to be, but I still usually carry my umbrella when there's even a hint of rain, and usually have an umbrella no matter what, because we aren't perfect at being able to predict the weather, because we don't have a way of being able to take data from lots of different sensors and fuse them at a national or global scale. Something, of course, that's very important for all of us who use cloud computing is having highly available business enterprises. When AWS or Azure or Google Cloud goes down, lots of things have ripple effects because we are dependent increasingly on the availability of capabilities that provide us with computing and communication. Something else that would be nice would be personal digital assistants, smart devices, smartphones, and so on, that actually assist us rather than just spying on us to try to sell us more ads or try to sell us more products. So that would be another thing that we need to continue to focus on. Something that's crucially important for many different reasons is be able to have dynamically integrated, secure, personalized, holistic, and affordable healthcare. And there's lots of challenges. Of course, we're hopefully kind of coming out of the pandemic, but one of the things that became clear during the pandemic was that the old way of doing healthcare, where you had people go to a hospital and have doctors and nurses running around on their rounds to give them monitoring and make sure that they take their medicine, that doesn't scale, especially if you can't have physical contact or you have to limit physical contact. So being able to do things like have chatbots that can help to monitor patients and make sure that they're coming out of their drug treatments properly if they come out of surgery, for example, being able to have remote patient monitoring that may be able to do an effective job of keeping track of people's vital signs, even if they're at home and not in the ICU or not in a hospital ward, or even just dealing with the fact that there's a nursing shortage these days. These are all things that motivate new innovations, especially innovations that are going to be privacy preserving, because that's important too. And then, of course, there's a whole range of smart stuff, smart cities, smart buildings, smart roads, smart cars, smart transportation systems, and so on. And these are all motivating the demand for new R&D advances, and middleware is very, very important in all those areas because we can't afford to build all those systems from scratch, top to bottom, like we used to decades ago. There's also a number of other trends. There's the issue of scale. Systems are getting bigger. Systems are getting more integrated. So we need to be able to have safe and resilient software composition. We also need to be able to rapidly and continuously evolve and deploy software and help it evolve, oftentimes in the field, because we can't afford to bring it all back to the shop and do it there. For example, if you are familiar with modern electric vehicles, there's ways of being able to apply software patches and updates without having to bring the cars back to the shop. One of the key challenges we face, certainly in the US, and I suspect this is true around the world, is workforce gaps in software talent. Even with the explosion in interest in computer science and software engineering in many universities around the world, we still don't have all the talented people we need to be able to provide the innovations necessary to support the never-ending growth and demand in capability. So we have to find a way to teach people and probably retool a lot of people later in their careers. And then there's also, of course, all the focus on artificial intelligence. We'll talk a bit more about that in just a moment, but things where we're using automation more effectively to do things that used to be done in a largely manual and ad hoc way. Something else that's very important is systems get more and more crucial, more and more mission critical, more and more safety critical, things like, again, driverless cars or hospital systems. We want to be able to make sure that we have correct evidence that systems behave as intended so we can certify these systems. Many of these systems are in regulatory fields where you can't afford to get it wrong. Things, for example, like medical devices, medical instruments, medical things like teleradiology or things that require telesurgery. Those things, you don't want to have those fail because somebody's had a blue screen of death in their computer system. Another key theme that's driving a lot of the trends are the fact that we're increasingly relying on so-called cyber-social platforms that influence our social behavior, our entertainment, our voting behavior, our sentiment as a culture or society, and trying to find ways to make those systems be less likely to be gamed or hacked, or exposing vulnerabilities in those systems that can mislead people through things like deep fakes. So those are examples of what we call societal scale systems that we have to be more and more cognizant of, because they're having an influence on more and more of our lives every day. And then something else I kind of alluded to before, but is worth repeating, data is becoming more and more important. And in many cases, data has become as important as code in modern systems. Think about data science or consumer data sentiment, consumer analytics, trying to figure out how to serve ads, for example. Data is crucially important, and there's many different dimensions to that. And once again, advances in middleware are crucial to support these trends and to support these new types of systems. We're not going to get there solely by using yesterday's operating systems, yesterday's protocol stacks. Things need to be more and more integrated using middleware as the glue to interconnect all the parts. So with that, let's talk about the future of software. And when I use the word software engineering here, I mean this in a broad sense. So developing software, testing software, deploying software, helping software evolve over time, optimizing software. And one of the key themes that is crucial to appreciate is that the way we do software now is increasingly going to be replaced or perhaps enhanced, hopefully enhanced, where we have software pipelines that consist of people like you and me, as well as AI, using again that term in a somewhat loose sense. Think about automation, perhaps is a better term, that is a trustworthy collaborator with people, so that we're in a better position to rapidly evolve systems based on statements of user intent, or put another way, higher level ways of specifying what we want to have done, rather than having to laboriously code all the solutions in a tedious and error-prone way by hand, the way that most of us have throughout the bulk of our careers as software developers or researchers. And achieving this vision requires advances in both development paradigms and also architectural paradigms. And let me talk about these briefly. So development paradigms are important to help improve the efficiency and productivity of software, and also the optimization of software, as well as the trust of software as we build systems at scale, especially complex, mission-critical, safety-critical systems. So here are some of the emerging themes that we're going to focus on in the rest of the talk. Humans being able to leverage trusted AI, again, using AI loosely, as a workforce multiplier, because we just don't have enough people to do it all manually, for all aspects of software creation and sustainment. Basically, that means across the software lifecycle. Another key area that needs to get better development and R&D is to have formal assurance arguments that can be combined and analyzed to assure and efficiently reassure continuously evolving software. And we're going to spend a lot of time talking about both of these bullets in a second, as well as this third bullet, which are enhanced composition mechanisms to enable predictable construction of software-reliant systems at increasingly large scale. Once again, middleware plays a crucial role in all of these areas, particularly, of course, the third bullet, which is where we spent a lot of our time over the past several decades as a research community, focusing on how to compose systems out of modular components based on various middleware platforms and frameworks and architectural patterns and so on. There are also advances in architectural paradigms that will enable the predictable and secure use of new computational models. And I'm not going to spend as much time on this. It's an interesting topic. It's not quite as germane to middleware, but it's very important. So very quickly, trying to figure out how we can build these large-scale, societal-scale, socio-technical systems. Think Facebook, think the metaverse, think all the social media platforms that you know and love, perhaps begrudgingly, and trying to figure out how we can integrate advances and insights and theories and so on from other disciplines besides computing, for example, from the behavioral sciences, economics, social science, psychology, in order to get more predictable and more desired outcomes. These systems, for better or worse, can be used for good or bad, and so we want to make sure that people use them as much as possible in ways that are going to be values preserving and not just there to titillate us, or not just there to convince us to spend money on things we don't necessarily need. Something else that's very important is how we can find ways to combine machine-driven AI-style components with non-AI components to interact in predictable ways to achieve various goals. So being able to ensure that intelligent systems behave as intended. And that's a huge, huge problem as we move more and more to machine learning-driven ways of solving problems and providing advice and doing analytics that guide behavior and so on. And then another interesting topic are new computational substrates. The most obvious one here would be the development of quantum-enabled systems. And I'm not going to spend a whole lot of time on that, just to point out that that's also a potential interesting area and something that certainly deserves our focus as a research community in the middleware space. So let's talk briefly about these advanced architecture paradigms, and then we're going to focus on the paradigms that have to do with development, because that is more middleware-centric in my mind. So engineering societal scale software systems, this is basically where we have to figure out how to integrate other domains, other disciplines to get their insights so we can build bigger and bigger systems that have more direct impact on our daily lives. Again, think social media, but it's bigger than that. Think metaverse, but it's bigger than that. And being able to find a way that we can put people and technology together that lead to predictable outcomes, where things work together in ways that we oftentimes don't really anticipate or control from a software-centric viewpoint. The engineering of AI-enabled software systems, it's becoming very clear that people are more and more ceding decision-making to software, and that software is often using artificially intelligent-driven models, machine learning, deep learning, transformer models, and so on, in order to be able to make predictions, in order to be able to look for trends, be able to classify patterns, and so on. And we have to be very cognizant of the fact that most times these days, people use these systems in ways where they don't understand what they do. And so we're at risk of creating a really vulnerable situation where our systems become more intelligent than they ought to be, and it leads to all these dystopian themes like Skynet and Ender's Game and things like that science fiction authors have written about for decades. And then I mentioned before the quantum computing focus, the new computational substrates. Right now, it's still, I think, probably fair to say that we haven't made a lot of progress on the hardware side of quantum computing. There's lots of interesting discussion of things like qubits and quantum states and so on. But let's assume, for sake of argument, we get to the point where those things actually do something useful. Then we have to figure out how to program them. We're going to have to figure out how to validate and assure them. We're going to have to figure out how to sustain them over the life cycle and be able to provide all the things that we do with middleware today for cluster computing, for cloud computing, but with all kinds of other properties in the infrastructure that we don't really understand yet. And I think this is going to be a very fascinating area for research if and when the hardware side of quantum ever takes off. So now let's focus on where we're going to be looking at the rest of the talk. And this is what we're going to talk about for the rest of the time. So AI-augmented software development, where we are going to be using AI tools and techniques to do a better job of building software. Talk about assuring continuously evolving systems, where systems have to evolve. We have to provide various forms of evidence that give us confidence the systems work as intended, as opposed to doing something we don't want. And then finally, software construction through composition, which, as I mentioned before, has been a very meaty and very useful research topic for decades, but there's some new twists that we need to think about in terms of R&D and advances in research down the road to address all the new challenges in these spaces and new opportunities. So let's start by talking about AI-augmented software development. So the basic idea here is to leverage all the advances we hear about daily about deep learning and transformers and search-based algorithms and so on, to make it easier and more predictable and more reliable and correct to build the next generation of software, to design it, to evolve it, to check it for conformance, to do certification and so on, so that we can build these software engineering principles into the system development in ways that computers do a really good job of, being patient, being thorough, being efficient, being scalable, and so on. So one of the first things to do here is to figure out what stages in the software lifecycle even lend themselves to AI. Are we going to try to replace the coding stage with things that are generated entirely from human-driven commands? Probably not at large, but there's certainly lots of places where you can make advances. For example, I've done some research with colleagues recently on ways to be able to take human utterances and then turn them into bash commands, and to do that in a way that is accurate and effective. And it's actually a research challenge to figure out how to come up with accurate natural language transformation from spoken utterances into things that would tell computers what to do so that people don't have to understand the obscure syntax of the Unix command shell. Being able to figure out who does what, whether people do certain things, whether computing and AI does certain things, being able to orchestrate that so it becomes predictable, it's built into the software processes. And then also something important, and I kind of alluded to that with my example about human speech to bash command translation. How do we understand human expression of intent? Humans are able to communicate very effectively, but that's because we also are able to deal with ambiguity. And if you don't understand something, you ask a person for clarification. Computers are oftentimes very literal, and so getting them to do the right thing with ambiguous statements is tricky, and we still haven't quite got there even after decades of looking into that. Now, the good news here is we're really just trying to focus on software development, not all aspects of artificial intelligence and natural language processing, so we at least have a fighting chance. But it's still tricky, and it's going to take some doing. So how do we design new phases, new activities? How do we rethink the way the software pipeline should be put together, the software lifecycle to support increasing automation? How do we figure out how to model these things and verify them? We'll talk about verification more in the next couple of slides. And one of the key themes that really is becoming effective here is how do we incorporate AI testing tools and certification tools that can keep track of all kinds of metadata from earlier parts of the life cycle, in particular things like test plans or specifications or requirements, and be able to percolate those things along in the software life cycle to make sure that what we evaluate in the later phases, when we're further down the road to having something that actually is runnable and workable, consistently carries through all the requirements and test plans and specifications that were done in the early phases. So the way to think about this is trying to essentially shift left but look right. You want to be able to shift things earlier into the life cycle to try to get issues resolved as quickly as you can through automation, but then make sure you keep track of those artifacts over time so you don't have discontinuities and disconnects. This is also another place where middleware is crucially important, because middleware is a great place to keep track of metadata and information that otherwise gets lost in a totally manual software lifecycle process. And then, of course, the other key theme here, which we're about to talk about in more detail, is how we can use artificially intelligent or basically machine automated tools to orchestrate continuous system evolution. So let's talk about that. So as systems get larger and as they live longer, they're going to have to be updated continuously over their lifetime. And it doesn't take much thinking to see this in practice. You think about modern websites where you want to be able to update the website over time without requiring people to have to download new clients or go out and buy new software and install it on their desktop or their laptop or their mobile devices. We see this all the time with systems like air traffic management or supervisory control and data acquisition systems to manage power grids. These are, and the telecommunication systems, of course, these are systems that really cannot have any downtime. You can't take down the power grid. You can't take down the air traffic management system and reboot it. You can't take down the global telecommunication systems. These things have to basically be updated in place. And as they get more and more mission critical and safety critical, we got to figure out how to do this in a way that will be cost effective. Because right now, especially for safety critical systems, it takes an eternity to make changes to stuff and get it rolled back out. And that is too long, and it takes too long to make sure things work. The thing that makes this particularly hard is we have to think about both functional attributes, normal requirements and specifications, as well as the quality attributes, all those ilities that we know and love in the middleware space. So if we want to be successful, we have to have advances in a couple of different areas. One is theories of evidence, and the other are theories of evolution. So theories of evidence really comes from the formal methods community, and nowadays there's many different ways of being able to evaluate whether a system is meeting its requirements. There are formal methods or semi-formal methods that involve proof systems and mathematics and so on. And then, of course, there's the stuff that most people actually do in practice, which is testing. And I think it's probably fair to say that people have figured out how to test at scale much better than they figured out how to do formal methods at scale. And that's because testing in the traditional ways of running regression tests and static analysis and dynamic analysis scales nicely as the number of CPUs goes up. And we're just starting to reach that point with formal methods. So there are people who work at various places like Amazon where they're actually using formal techniques. There's people places like Microsoft, for example, where they use formal techniques to evaluate certain aspects of code, and continuing to evolve and integrate those things is crucial. The other part that's important here is the theory of evolution, understanding how changes to the systems propagate and possibly lead to new failure modes or new vulnerabilities. And this is what makes this area so difficult, especially if you're trying to evolve a system as it runs, because you really don't want to unleash new software, new patches, new bug fixes without knowing what the consequences are. And that's difficult because there's so many hidden interactions and vulnerabilities that people are only vaguely aware of, because humans have a very hard time keeping it all in their heads. So that's an area where automation will become important, hopefully some AI as well, and being able to automatically generate and analyze data and metadata, and then generate improvement suggestions automatically based on longer-term analysis of system stability properties and so on, and assurance cases will be invaluable. As we talked about before with the AI areas, being able to combine human expression of intent with generation of data and storage of metadata and so on in order to generate and assure change requests will be absolutely important. And once again, we can't expect the whole world to learn to program in Z or other formal method approaches. We have to find a way to be able to let people specify things in a more human-centric way and then generate down and synthesize and so on the various parts. This again is a middleware perspective more from a tooling point of view than perhaps a runtime point of view. And then of course something else that's really important is these systems get large and we want to make sure that we don't field solutions that are full of bugs to the detriment of unsuspecting users. We'd like to be able to do the automatic generation of evolution trajectories. This is what's often known as hypothetical analysis or speculative analysis. You say, what would be the effect of making the following changes and deploying these changes into our infrastructure under these assumptions? And then you'd like to be able to do some kind of simulation or emulation to know what the consequences will be before you release the software into the wild. And needless to say, that's crucially important in mission critical and safety critical systems. It's also important in highly available business systems as well, where downtime costs money. The last topic area, and then I'll wrap up, is one of my favorite because I've worked in this area for a long time, and this is software construction through compositional correctness. So I would hasten to say that one of the biggest contributions of middleware over the past 3 or 4 decades has been allowing people to build systems out of modular pieces that can be glued together using middleware as the glue. And the goal, of course, has always been to be able to build systems that are more robust and more resilient than their individual parts when considered in isolation. And a great example of this would be the TCP/IP protocol, where the IP layer expects and anticipates failure, but then you layer a TCP layer on top of the IP layer, which provides you with end-to-end reliability. So the end-to-end behavior of the system is more robust and stable than the part-by-part or the hop-by-hop piece. If you want to be successful here, it's going to require several things. We need new and improved theories of composition, as well as better focus on patterns, especially architectural patterns that help to figure out how to integrate things at scale in an intelligent way. And then the other thing that's still missing are integrated tool chains that can assure various properties across the system and across time. So kind of going back to the previous point about being able to assure systems continuously as they evolve, we'd like to be able to build them out of pieces where you can make changes to pieces and then not have to reassure or recertify the entire system, but only the parts that are affected by the pieces that change, which of course is a modularity argument. And that's absolutely perfect for middleware, and thinking about ways to do that at scale is crucial. And we'd also like to figure out a way that the cost and complexity of assuring these complex systems built out of modular parts doesn't grow more than linearly with the size of the system and the scope of the changes. So right now, if you have systems built out of modular pieces, if you're not careful, when you make changes, you have to go back and pairwise recertify all the pieces. And of course, as the number of pieces goes up, that pairwise certification and revalidation grows at least quadratically, if not higher. So we'd like to figure out a way to keep the scale of the complexity of composition down. Something else that's important here is to think about compositional correctness in more ways than just the classic API syntax and semantics. We're very, very good in the middleware community of figuring out ways to reason about our APIs in terms of the syntax and in terms of some of the semantic aspects through various tools like assertions and preconditions and postconditions and invariants and so on. That's something that's been around for many decades. But there's a number of cross-cutting attributes that are much more difficult to analyze by focusing only on the APIs in isolation. And these typically have to do with ilities that are important, things like the timing properties, the fault tolerance properties, the security properties, where no one element in the system is contributing to the success or failure of the whole thing. They have to work together. And many systems over time have failed because of the inability to understand those ilities and reason about them in a cross-cutting way. Something else that's crucially important is to continue to figure out how to build these systems at scale and then look for recurring themes that can help us to codify them in the form of patterns and then ultimately automate them in the form of tools that can specify and enforce composition rules about how things get glued together. And a lot of these things today are increasingly not coming from one source. They come from many sources. So being able to assure the sources that are often third-party sources, often open source sources, is very important. And especially if you want to go to a kind of a microservices model where things get integrated in a very late binding way, doing that with existing middleware techniques is still kind of a black art and not a science. Something else that's important, it's kind of captured with all the things I talked about, are smart composition tool chains that can do the analysis at scale. And right now, again, we have different people, different researchers, different companies that provide piece parts, but an integrated tool chain that works for many different languages, especially the languages that are commonly used today, still remains elusive. Okay, so let's kind of wrap up and then I'll take questions. So I strongly encourage you to go out and take a look at the study. It has lots of interesting discussions. Here's a summary of the findings of the study. So clearly, software development, software engineering, software processes, software methods and tools, and so on profoundly impacts all the aspects of society that we know and love. We rely on this technology daily. If it doesn't work, we certainly start to panic. If your phone doesn't work or you lose internet connectivity, you probably start getting some kind of a twitch because it's very disturbing. Key issues that will impact the future directions in software and middleware include smart automation, the assurance and reassurance of evolving systems, understanding how to compose systems in an intelligent way, all those new types of systems that I talked about, especially things that are going to be increasingly autonomous, focusing on integration of heterogeneous systems at ever larger scales is very, very important, something that the research community struggles with because oftentimes we don't have the kind of funding or the kinds of opportunities to work at scale. That's where partnerships come in. That's where focus on being able to do work at scale with challenge problems becomes important. And we also have to think about more than just the technical aspects. As you all know, people have been looking at things like deep fakes, which is the application of technology to impersonate somebody. There's also the whole issues of using social media platforms to try to spread propaganda. We see this all the time now with things like global conflicts, with elections. We have an election coming up tomorrow in the US, all kinds of issues about the role of big tech or social media platforms in influencing people's voting behaviors and people's sentiment and so on. This is something we can't do in isolation. We need to have collaboration with government. We have to work with industry. We have to work with other universities in a global way. So these types of conferences, of course, are crucially important. And researchers of tomorrow, which doctoral students, of course, are, really need to think about collaborations because it's going to be hard to do it by yourself. Moreover, it's going to be hard to do it without interactions with other communities outside of traditional technology fields. So social science, medical science, medical practice, law, economics, business, these are all places that we can make a big impact by working together. Something else that's important for those of us doing work that goes across boundaries, we have to figure out ways of being able to support seamless integration across geographic boundaries, across computing boundaries. Very few people today, especially in the post-pandemic world, or hopefully becoming the post-pandemic world, go into work and work with a team face-to-face 24/7. They typically do things more remotely. So finding ways to make tools be more effective to help coordinate interactions of people and technology and artificial intelligence and so on is crucial. And then, of course, we also have to think about, I think we have a big responsibility to figure out how to meet the growing needs in our workforce. More people need to be computing literate. They need to be able to at least understand the consequences of technology, even if they're not software developers themselves. But we have a lot of people who are becoming software developers, but the world they're going to work in is going to be very, very different from the world that many of us, especially the older faculty, grew up with when we were grad students and we were first assistant professors where we went to our initial institutions. So a lot of things are changing, and we have to be willing to rise to the occasion and think about new ways of teaching, think about new ways of lifetime learning and new ways of being able to take the research that we do and find ways to transition it into practice. So that's the end of my prepared remarks. I'm happy to take any questions if you have some.